So after discussing the previous chapter, which is electrochemistry, let us turn our attention to the new chapter, which is chemical kinetics. The name itself suggests that this chapter is related to the speed of the reaction. And for the very first time, we are introducing this particular term, the speed of the reaction. And in this chapter, we are going to decide that how quickly or how slowly a chemical reaction actually takes place. And it is due to so many factors, and we are going to discuss on those factors only. So again, I'm telling you, it is a new dimension altogether. We have never introduced the speed of the reaction before this particular chapter. So let's see, it's a mathematical one. There are various numericals as well as the mathematical expressions. We have to be very careful. We will not only the deriving the particular chemical equations, but we have to understand the physical significance of each and every chemical equation. So let's see. So if we want to say anything about the chemical kinetics, we will write it is, you can say it is branch of chemistry which deals with the speed, or you can say the rate of a chemical reaction, and the factors associated with. So this is what we need to understand, that is the rate of a chemical reaction. So our next topic will be the rate of the chemical reaction. So let us talk about rate. So in order to understand the rate, let us see two different reactions. One is, say, we take NaCl plus AgNO3, and in another case, we take, say for an example, CH3CO2H plus NaOH. So we have taken both these reactions. Let us see what is the speciality. In this case, the product is obvious, NaNO3 plus AgCl, and in this case it is CH3CO2Na plus H2O. So needless to say, the first one involves the ionic compounds, so it is much more fast. It is a faster reaction and it is comparatively slow. So we are now discussing about the speed of the reaction, which one is fast and which one is slow. So since we have already mentioned the speed of the reaction, the speed depends on rate. So let us now understand what is the rate of the reaction. So let us revisit. So while discussing the rate of the reaction, we have taken a very easy and understandable chemical reaction R giving rise to P, which is obviously R is reactant and P is product. Now, few things must be mentioned before we move on. First is, obviously it is reactant and it is product. So initially, let us the reaction starts at T1 and finishes at T2. So first thing first, time taken should be written as T2 minus T1, which is delta T. Now, as a matter of fact, Let us talk about this side. Initial reactant concentration is R1. Remember, this third bracket suggests the concentration, and the final reactant concentration is R2. So if we want to write the change in the concentration of reactants, it should be R1 minus R2. Now, if we want to define rate, rate should be defined as, there are two ways. I'm writing both of them. And before I write this, here similarly, if initial product concentration is P1 and final product concentration is P2, then we should write change in product concentration obviously is concentration of P2 minus concentration of P1. So we have mentioned all these things. Now let us talk about rate. When we are talking about rate, it can be written in two ways. First is disappearance of reactant by time taken, which can further be written as, see, it is R1 minus R2 divided by time taken is delta T, which can be written as minus delta R divided by delta T. So here we should write that it should be, here it should be R2 minus R1. Should be R2 minus R1. Here also it should be R2 minus R1. Like P2 minus P1, just a small rectification. So the answer should be minus delta R divided by delta T. The negative sign has been introduced. This particular negative sign has been introduced to make everyone understand that R1 is obviously greater and R2 is obviously less. And this negative sign denotes that we are talking about the reactant side, not the product side. Because with time, the reactant is going to decrease. The concentration of reactant is going to decrease. So if you are checking the disappearance of reactant, it should be negative. Similarly, in case of products, the second case, this is the first case, okay? In the second case, we should write the appearance of product divided by time taken. So this is also rate. This is also rate. Now, as a matter of fact, it can be written as, if it is not visible from here, you see, it can be written as appearance of product means with time, how much product is going to change, how much product is going to be formed, that is P2 minus P1. So it is P2 minus P1 divided by delta T, which is nothing but concentration of delta P by delta T. So again, let me repeat that we are talking about rate. We are talking about disappearance of reactant by time taken or the appearance of product by time taken. So in both the case, final minus initial, here just you change little bit, which I have written mistakenly the opposite one. So here it is R2 minus R1, here it is P2 minus P1 by delta T. But there will be a negative sign since R1 is greater than R2. Because the rate, obviously, initial reactant concentration will be higher than the final reactant concentration. So as a result, we are getting these two, and this is how we define rate of a chemical reaction, either with respect to reactants or with respect to products. Now, let us see few more cases regarding the rate of a reaction. So, suppose for a chemical reaction where this kind of reaction takes place, suppose PCl5 gives rise to PCl3 plus Cl2. There, we should be able to write that rate, which is represented as R, is minus of delta of PCl5, concentration of PCl5 divided by delta T is equal to delta, means the concentration of PCl3, change in the concentration of PCl3 divided by delta T is equal to change in the concentration of chlorine divided by delta T. So all of these were having 1 mole each. So this is how we used to write, and it is very simple. But if we introduce different coefficients, different stoichiometric cases. If we introduce different stoichiometric cases, then let's see what happens. There, we should be able to write, suppose we take the reaction first. We take A plus B giving rise to C. Suppose. Now, obviously, if we need to write down the rate, it should be minus of delta of A divided by delta T is equal to minus of delta of B divided by delta T is equal to delta of C divided by delta T. As a matter of fact, if it is so, when it is all of them are having 1 mole, if I change here as 2, if I introduce here 2, then you see we can write that 1 mole of this is giving rise to 2 mole of C. What is the immediate outcome? If we prepare 2 mole of C, then we should be able to write, say, rate of appearance of A and B are same, rate of disappearance. Rate of disappearance of A and B are same, but rate of appearance of C must be twice the rate of disappearance of B as per the coefficient. I repeat, it should be rate of disappearance of B should be is equal to rate of disappearance of A should be is equal to rate of appearance of C. It should be same when there was only like this, but when there will be an addition of 2 as a molar coefficient, so obviously these two will be same, but rate of appearance of C should be twice the rate of disappearance of B, and it should be twice the rate of disappearance of A also, because the disappearance of B, the quickly it disappears, this will form obviously at a much faster rate. So the rate of appearance of C should be twice the rate of disappearance of D. So obviously this equation then can be reduced as 1 by 2, because you see, if we are talking about the similarity between the two, then you can see 2 will be multiplied here. So if you look into the differential form, this 2 will be going here, which we have written as 1 by 2. Now, so this is all about this particular reaction. If we talk about any reaction, say for an example, if we talk about the reaction of N2O5, 2N2O5, if we write 2N2O5 gives rise to 4NO2 plus oxygen. In that case, same thing should be applied. We should be able to write down R is equal to minus half, this should be N2O5 divided by delta T. It should be 1 by 4, so it should be delta of concentration of NO2 divided by delta T should be is equal to, there should not be anything, 1 only, delta of O2 divided by delta T. So this is how we can write down for any reaction depending on the molar coefficients. Now let us talk about the next segment, which is average rate and instantaneous rate. So next topic is average rate and instantaneous rate. First, let us talk about average rate. Average rate is the simplest one. It is the change in concentration of reactant or product divided by time interval. So this is how we used to write. So average rate average should be written as delta R by delta T when there is a negative sign and there is this third bracket. Or we can write delta of P divided by delta T. This, for this particular reaction, are giving rise to product. But whenever we are talking about instantaneous rate, then it is the rate of a chemical reaction measured at a particular instance or a particular moment of time. Or you can say it is the rate of change of concentration of any of the reactants of products. So let me write down, it is the rate in change of concentration of reactants or products. We should say any reactants or products at a particular time. When we are talking about this term, the particular time or particular moment of time rather, it will be much better to understand. Particular moment of time. That means we are basically talking about a very little time gap. So that is why we consider delta T tends to 0, means very, very less amount of time. The change is the change that takes place, the T1 and T2, the difference that we used to write, here it is almost tends to 0. That means very less amount of time, at an instant. So as a result of it, we should be writing down the rate, or you can write instantaneous rate. Simply R, if we can write, it should be or R instant if you write, it should be like this. The delta should be replaced as D, and this is R, and delta T will be replaced by D as well. So dt is equal to dP by dt. And from here on, we are going to utilize this only. That means whenever we are going to talk about R, we are basically going to talk about the instantaneous rate from here on. So as we have mentioned, for this particular reaction, the instantaneous rate should be written down like this. Remember, we are considering delta T tends to 0. Now, if we take a particular reaction, say for an example, we will check two cases. For the first, the generalized case. So generalized case means we are considering this reaction, which is A of A plus B of B, giving rise to C of C plus D of D. Remember, all these are what? These are molar coefficients. Now, if we want to write down the instantaneous rate, it should be minus of d of A by dt is equal to minus of d of B by dt is equal to d of C by dt is equal to d of D by dt. But remember, we have earlier seen that in case of, if we can remember A plus B giving rise to 2C, this 2 was becoming 1 by 2 in this differential equation. So here also we are going to do the same. It should be written as 1 by A, it should be written as 1 by B, it should be written as 1 by C, and it should be written as 1 by D. And that is how we can write down the generalized case. So if we can write down the generalized case, for a particular case also, we should be able to write. So now let us see the particular case. That is, suppose N2 plus 3H2 giving rise to 2NH3. So this is a particular case. If we can write down for this reaction, we should be logically should be able to write down for any reaction. So in this case, if we want to write down R, it should be, check, it should be minus of concentration of N2 divided by dt is equal to minus of concentration of H2 divided by dt is equal to d of concentration of ammonia divided by dt. One thing, here it should be, here it is only 1, but here it is 1 by 3. So I should be able to write down 1 by 3, and I should be able to write down 1 by 2. So this is how we are in a position to write down the rate. We have seen the slowly how we have evolved. We have initially written down the average rate, then we have written down the instantaneous rate. So it should be written down like this from here on. So this is the beginning of this chapter, basic things. Slowly some more terms will come, but first you need to understand this. Now, whenever you see any chemical reaction, you should be trying to write down this type of differential forms. We should be able to write down the instantaneous rate for any reaction under consideration.